And then I'll just do a brief introduction to welcome everybody, and then I'll turn things over to you, Liam.
Sure.
So good morning, everybody, and welcome to the March edition of Trainee Talks. Trainee Talks is a series of research talks delivered by software engineering graduate students in our CREATE SE for AI program, who are receiving specialized training in the technical and social aspects of AI-based software systems. My name is Lori Akiyama, and I'm the program coordinator for CREATE, and I'll be moderating the webinar today. And today we are very pleased to introduce two of our master's students, one from Queen's, one from Concordia University, to deliver their research talks. And I'm really excited about these talks because these students have been amazing contributors to our program, and they're going to do amazing things when they step out into the world. So first off, we have Liam Johnston. Liam is an MSc student in software engineering at Queen's University, supervised by Dr. Ying Zhou. Liam's research focuses on improving software maintenance practices using AI-powered approaches. And Liam will be presenting his work on LabelMate, an LLM-driven framework for refined issue report labeling. After Liam's presentation, we're going to hear from Caren Rizk. Caren is a master's candidate in software engineering at Concordia under the supervision of Professor Imad Shihab. Her work explores how large language models can jointly reason over user stories and visual design artifacts to synthesize dynamic React applications. Her broader interests include AI-assisted software engineering and human-to-AI collaboration in development workflows. Caren's talk is on bridging design and implementation, a study of multi-agent LLM architectures for automated front-end generation. So each trainee will speak for 20 minutes, and then we'll have time for questions afterwards. And with that, I'd like to turn things over to Liam.
All right. Yeah. Thanks for that introduction, Lori. And I will share my screen here. Oh, you got to enable me to share my screen, Lori.
Oh my goodness. Okay.
No worries.
Sorry. Now you should be able to share.
Perfect. Yep. Got it.
Okay, great. Thanks.
All right. Can everyone see the screen? Perfect. All right. Yeah. As Lori said, my talk is on LabelMate, an LLM-driven framework for refined issue report labeling. So just for some background on issue report labeling, the benefits of it include that they attract significantly more attention than unlabeled reports. So that means more subscribers, assignments, and comments. So more people are willing to solve those that are labeled. And another thing is that they're resolved more efficiently too than those that without labels. But only 50% of issue reports are actually labeled in practice that many studies have found. So why is that? And the biggest things that we find are that there are adoption challenges to labeling. So the first one is that deriving a label as suitable for a given project can be a significant barrier to entry because you have to understand your project's structure and workflows and anticipate the types of issues that may arise. And then another thing is once you have this list, assigning relevant labels from it to new issue reports can also be labor intensive and time consuming because you got to read through them. You got to say, all right, which of the labels in our list fit? There might be many labels, right? So yeah, these can be time consuming tasks. And because of this, there have been approaches to try and automate these processes. So this is one for simplifying label creation. It uses topic modeling basically to cluster historical issue reports into different topics. Then you get keywords for the topics. And then from the keywords, you can decide which labels that you want. But there's limitations with that, right? Because you have to predefine the number of topics or labels. So you have to decide, all right, this is the amount of clusters we want. And then in turn, that may limit how many labels you can get from it. And again, all it produces is keywords. So you have to decide what the labels are. You're not going to know what the labels are right from the get-go. And for automating label assignment, there's been tons of approaches on this, but a thing that a lot of these approaches do is they only limit it to assigning one of four, up to four labels. Sometimes it's only two of them. Sometimes there's three of them. But yeah, they're usually one of the four: bug, feature, question, or documentation. And real world projects use a lot more fine grained labels. I have some examples there up on the screen: security, compiler runtime, performance, and refactoring. So as a result, like, these haven't really been adopted because they just don't have that usefulness that categorize issue reports into more fine grained categories. And so this one actually does do that. It pre-trains its BERT models on actual labeled issue reports. But the problem with that is that it requires the existence of a consistently large and sufficiently labeled database for the project. So your issue reports already have to be labeled correctly so it can learn from that, and then it can use that to label new issue reports. So that doesn't really mitigate the adoption challenges because you've already needed to have a consistent labeling practices. So that's where our approach comes in. This is a high level design. We're going to get into more of the components a little later, but basically the idea is all you need to adopt it is historical issue reports. Then we generate some candidate labels, we refine them, we consolidate them through these 3 steps, which I'll get into later, and then we get a label list. So basically all you need to provide, like I said, is those historical issue reports. You'll get a list, and then we have a mechanism to assign labels from our list to the issue report. And we also even have a RAG-based component but you don't need to provide the database in advance. We provide a way for assigning the labels, ensuring that they're validated, and then you can learn from these past labels to assign new labels to issue reports. So yeah, just to talk about how the data set we use, we started off with we mined 16,500 issue reports from 30 popular repositories. And then we did an 80-20 train test split. So the train set was 13,210 issue reports. These act as the historical issue reports used to build the label list and build the RAG database. So this is the idea of, if you're going to use this in real life, this is the issue reports you'd have before. And then the test set represent the newly submitted issue reports that we use to label. And then another component we have is the label assigner LLMs. These are used to generate the candidate labels that are refined to derive a label list and assign labels from the generated list to new issue reports. We use these 3 models, Gemma 2, 9 billion instruction tune, Llama 3.1, 8 billion instruction, and Qwen 2.5, 7 billion instruct. And the justification for choosing them is, one, that they're instruction tuned because these prompts can be quite challenging to understand. So this ensures that they're more robust in adhering to them. They're open source, which ensures reproducibility and accessibility for use. And then the moderate parameter size also provides an effective trade-off between performance and computational cost. So that's why we picked them. And then another component is the label evaluator LLM, which we actually use to evaluate the accuracy of label assignments. We use a bigger model, DeepSeek reasoning, 70 billion. And a justification is we want these reasoning capabilities because this allows us to look into like why it judged a label to be accurate or not. The larger parameter size, although that means it's a little less accessible, we only apply it for evaluation, not labeling. So that means it's not used as much. So it gives you a little trade-off between the two. And again, it's open source too. So that it ensures continued ease of accessibility. So first we conduct a motivational study looking at how are labels assigned to issue reports by LLMs without a predefined list, because we talked about the list earlier, but this is to look at what happens if you don't have it. What happens if you just ask it to assign any labels to an issue report, basically. So we start off with our train set, and then we get our 3 label assigners to assign labels, and this is what we get out of it. So for some findings, you can see that an excessive number of labels are generated. So we did apply some label post-processing to try and get rid of basically just lexical differences. So there's a few of those that we post-processed for. But again, you see here that for 13,000 issue reports, like even the smallest number here, which is Gemma, generated almost 6,000 unique labels. That is very impractical to apply in real life because you got to pick from 6,000 labels. And then it doesn't even really give effective categories that way either, because if you have 6,000 categories, most of the categories are going to be kind of meaningless. So That's the problem there. And then another one is the percentage of unique labels generated from only one issue report. You can see that around 60%, it's 60% of these labels are only generated from a single issue report. That means that they're not categorizing anything. They're overly specific. And again, the point of labeling is to categorize things. So that doesn't really make a lot of sense to have labels that are only categorizing one of 13,000 issue reports. And then the last one, which you can't see from the table, but LLMs generate different labels with similar meaning or synonymous labels. So that also would affect the label list, because then you decide, oh, which one of the two that kind of mean the same thing do I pick to assign as a label? That unnecessarily inflates the label list, and we don't want that. So yeah, those are some problems right away with if you just let the LLMs freely assign labels. So from this, we come up with research questions. The first one is about how can we make a label list that is suitable. The second one is we just let the LLMs assign labels from the list. The third one is where we introduce our RAG-based pipeline. And then the fourth one, we look at how our label list aligns with other label lists of projects that weren't in our data set. So I'll start off with RQ1 here. We have a 4-step approach. First, we process the labels, we group the labels, we select representatives of the groups, and then we evaluate the representatives. So for step 1, process labels, we basically first pool the labels generated by the label assigners in the motivational study. That gave us 14,000 unique labels. And then we exclude all labels generated by one model for a single issue report because, like I said earlier, these fail to represent shared issue types. That chopped off about 8,000 low-frequency labels right away, leaving us with 6,000 for consolidation, which brings us to our next step, the semantic grouping of labels. So first, we compute embeddings for the labels, and then we cluster the embeddings using that algorithm I have up there, agglomerative clustering, which basically iteratively merges the closest clusters until a termination condition is reached. And we set the termination condition to when no pair of clusters exceeds a certain distance threshold, which we have as tau on the slides. And then the pairwise distance between clusters is calculated using cosine distance, which is the angular separation between two embedding vectors, and average linkage, which is the mean distance between all pairs of points in the two clusters. We tried a bunch of different settings, and those were the ones we landed on. And then this is the resulting clusters. So we tested it from distance thresholds from 0.2 to 0.8, going up by 0.1 each time. And at tau equals 0.2, we found conceptually distinct labels in the same cluster. That was a cluster there with these three labels like regression, quantization, image processing. And at tau is 0.4 or greater, we found unnecessary fragmentation. That's like separating documentation and docs. That means the same thing. Segmentation, seg fault. Seg fault is just kind of short for segmentation fault. So I find that the optimal clusters are yielded at tau equals 0.3. And when we look at the summary statistics there, that's pretty indicative of dense clustering, right? There's 11 labels per cluster on average, median of 8 labels per cluster, which shows that there really is a high degree of synonymy in those LLM-generated labels in the motivational study. So this kind of reinforces why you need to give it the list. You need to give it the options, because if you don't, then it'll just go wild and, assign different things that mean the same thing. So after that, we select a representative for each of the 529 clusters from that clustering configuration. And we chose the label that's most frequently generated during candidate generation as the representative because it's the most common. So that worked out that way. And this ensures that only one label per concept is retained. So we reduce the redundancy and prevent the synonymous terms from inflating the list. So then after that, when we looked at those labels, we saw that many were names of tools or infrastructure. I have some examples up there like Java or CSS, which are programming languages, operating systems such as Windows or Android, that sort of thing. And we excluded those because they describe more implementation context rather than the functional or conceptual nature of the issue. That's what we were more looking at, is looking at the type of issue, not just what tool it affects. And so because of that, we excluded 254 labels, resulting in a final list of 275 labels. So now for the next one, RQ2, we're just looking at how do LLMs assign labels to issue report from our list. And what we do is we compare it against the 4-label approach. So we had the same LLM assign one of the 4 labels: bug, feature, question, or documentation. That was the most common one that I showed you guys earlier. And the original labels assigned to the issue report. And we evaluate by measuring the semantic alignment between the assigned labels and the issue report context using cosine similarity of their embeddings. Reason we do that is if the label and the text have more similar embeddings, then that probably means that the labels are more related, so it better describes the issue. We evaluate this on the train set, and here are results. That's a big table, so I'll kind of break it down for you. We also did some ensembling there too, as you can see. So there's unanimous between 2 LLMs, majority voting between 2 LLMs, and then unanimous voting between all 3. So that was something that we looked at too, to see maybe if we combine their decisions, it leads to higher alignment. So the first thing we find is that the Quen model without ensembling using the labels from our list has the highest overall alignment. That's great. We also find that labels assigned from our list are more semantically aligned than those using the 4-label approach. As we can see here, the worst performing configuration with the derived list is llama on its own, 0.147, which is better than the best performing configuration using the 4-label approach, which is 0.136. So that worked out well for us. We're also more semantically aligned at assigning labels from our list than the original labels. So the original labels here is 0.171, and 5 of the 8 configurations using our derived list have a higher average cosine similarity than that. Yeah, and then the last one is the agreement between label assigner LLMs ranges from moderate to almost perfect across various labeling configurations. So it goes to show that they agree most of the time on what labels, even from our list of 275 labels, a lot of the time they still agree on what labels should be assigned. So that's a good thing, right? That means they're pretty, even though they're different models, they're assigning mostly the same labels, which is good there. Yeah, so now the next one is the RAG-based component. So the first step is we construct the RAG knowledge base. So basically, since RQ2 is on the train set, we can use that as our knowledge base because those are representing our historical issue reports in this. And we use the labels assigned by Quen using our derived label list as the foundation because they have the highest average cosine similarity. And of the 30,000 labels that are assigned through this configuration, 87% were judged to be accurate. And then so the accurate labelings formed our RAG knowledge base. And then for the automated label assignment evaluation methodology, we evaluated on about the 3,000 issue reports in the test set. So for each issue report in the test set, we retrieved the K issue reports and the knowledge base with the most similar embeddings and their validated labels. And we tested various K values. And then we experiment with 2 different prompts using the retrieved information. One is labels only. So the LLM is instructed to assign the most relevant labels, and all we give it is those retrieved labels from the K issue reports. And then the labels and issue reports prompts includes both the labels, but it also shows which of the issue reports the labels were assigned to. So that way there's a little bit of added context there. So first, this is the similarities. We test this on average cosine similarity again, and the number of assigned labels for the 2 different prompts. And we can see here that both of these achieve their highest average cosine similarity at K equals 3. So that's the optimal number of retrieved issue reports for this. And yeah, and we also see that the labels only prompt has a higher average cosine similarity too. So maybe what this can kind of show is that the extra information, including the issue reports, kind of bogs down the prompt and it doesn't do as well. So yeah, and now for this, we compare it again. We compare it to the original labels assigned in the test set, the 4-label approach for the test set, and then including the full list instead of this subset retrieved using RAG. And we compare this performance. So while the full subset achieves the higher cosine similarity, we actually see here that when we look at what the evaluator says, we have 3 metrics here: overall label accuracy, which is just how many, the percentage of labels that were accurate; label accuracy per issue report, which is the proportion of each issue report's labels that are accurate; and then the percentage of issue report where all the assigned labels were accurate, they actually have higher scores than the full derived label list here. So we can kind of say that the RAG-based approach has higher performance. And the other thing with the RAG labels only prompt is that because it's only using the validated labels from historically labeled similar issue reports, the prompt size is a lot less. So you can see here that from k equals 1 to 30, we see a reduction in prompt size from about 68 to 65%. So that means we're using less tokens, and that's another added benefit of using that approach versus passing all 275 labels. And for the last research question, we looked at how does it align with the label lists of existing software repositories. And what we did was we measured the percent coverage of our label list relative to the existing one. So basically, we look at every label in the original list, O, and if there's a similarity, if there's one label in our list that has a similarity past this threshold here, then we say, okay, this label is covered. We measure the percent of labels that are covered. So here, this was our experiments here. So we tested two label lists that weren't in our, or from projects that aren't in our data set, because that way we're not reproducing the same labels. And we see here, like, as the similarity threshold gets higher, clearly it's only going to really keep exact matches. But at lower similarity thresholds, we find pretty high coverage, right? Even at 0.4, we're over 60% for both. So that goes to show that they're fairly covered. And then this is actually specific labels. So all the labels in the two project label lists that are above 0.7 I have here. So we can see some exact matches like release, bug, cleanup, optimization. And then the similarities are a little lower just because of lexical differences, because they have like category prepended to the front of these two or component prepended to APIs, whereas ours is just API. But it goes to show that some labels generated from ours can be transferable to other projects. So yeah, just to summarize what I have here, we went over issue report labeling, what's good, why it's less common because of the adoption challenges, how our approach can mitigate these adoption challenges. We showed that it works better than the original labels, the 4-label approach, existing work, and we showed that how labels from our label list can be used in real life. So what this kind of implies is that collaborative software projects seeking to improve their label taxonomy can either adopt our curated list of 275 labels. They're derived from 30 diverse software repositories, or you can generate your own for your own projects using our pipeline to ensure that your labels reflect the issue landscape of your own repository. So yeah, that's what I got for you guys today. That is my email in case you want to email me, and let's open the floor for questions.
Thank you, Liam. That was amazing. We have time for a couple of questions. Rashna, please go ahead, and then Anthony. Oh, sorry, you were clapping. Rashna, do you have a question? Rashna, you're on mute, so please unmute yourself if you have a question. Wow, no questions for Liam. Everybody understood.
I have a question. Liam, thanks for the nice talk. Sorry, I had to step out for a small part of it, but maybe you covered this. So you might actually get a lot of labels. How do you like for an issue report? So how do you do the pruning? I know you did the clustering to try and determine what is the optimal stuff like that, but of course, as you can imagine, that's going to change or be impacted by the data set that you use.
Yep.
Do you ever like prune the number of labels? And the reason I say that is because in some cases you might have a label that will apply to everything, right? So programming languages sometimes are a bit of that. Or if you have very common components like UI, you might get that across multiple. I don't know if you saw that in your data set or if you ever tried to prune the labels as well.
Yeah, so the way that the pruning worked was, so through the clustering that we just took one label per cluster, pruned a bunch. And then maybe when you stepped up, the other thing that we did was when I'll go back to the slide just so you can kind of get the idea. But yeah, so after that, after we pruned this, so this was one pruning where we only picked one label per cluster, right? Because obviously cluster, everything's shared. And then the next pruning we did was we got rid of these like that are just names of tools or infrastructure, just because we wanted to look at only the concepts rather than the rather than just what technology it's based on. So like I kind of
You
said,
got rid of those manually? Sorry, just
yeah. So we had two of us, and we just made sure we both agreed on them. But yeah, I mean, it pruned from 14,000 because basically we started from this, right? We had all these labels. This added up to 14,000, and then through the clustering and the pruning, it dropped us down to 275. So 275 that we know there's no redundancies because we did the clustering, and that there's describing the actual something that's actually the nature of the issue basically through this pruning. So yeah, that's how we did that.
Okay. So I think that makes sense, especially for the study part of it. But like I'm envisioning like if I was to use this technique, right? So in a tool.
Yeah.
And I inject the data set into it. Probably, you're going to generate some labels and things like that. Then in that case, it might not be possible or even desirable to do this manually, right? You're going to have to do this somehow automatically.
Yeah, and that could be a way
Does that
to
make
do
sense?
things
Or
like, yeah, I understand what you're saying. It might be a pain to go through that, but I guess the difference is that right now, what a lot of people do is like, oh, okay, we have to think of what labels we want. This at least eliminates having to come up with the idea yourself. You have lots of ideas because the candidate labels are generated there. So you're not starting from nothing now. Now all you have to do is kind of pick the ones that you want, right? As opposed to just starting from nothing and saying, oh, what would be good labels for my project? So that's kind of the idea there.
Gotcha.
Yeah.
Maybe just a second quick question. I don't know if other people have questions or not, but and you may have covered this, sorry, because I had to step out just for a bit. Did you ever look at what happens as your project or your data, let's say, evolves over time?
Yeah, no, that was that we couldn't do, right? We had our fixed historical, which was the train set, and then newly submitted, which is the test set. So then that would be the idea where it's like, okay, our project's kind of drifted. We're in a new space now. Then maybe we need a new
Or
set
just
of labels.
evolved, right? New
Yeah.
components,
If your
new
project
labels.
evolves so much where where the labels aren't useful anymore, then that would kind of be the solution we have for you based on what we have in this work. Maybe in future work we can come up with a better thing for that doesn't involve just redoing it all over again, but that's kind of the best solution we have for that at the moment.
Okay. I mean, I think you can, update.
Yeah.
Anyway, yeah. All right. I think you get it. All right. Thank you.
Yeah, I got you. Thank you for your questions. Diego, you got a question?
Yes, real quick. Thank you, Leon. I jumped in middle of your talk, so you may have already addressed this, right? But are there, let's say, software projects in which you would not recommend using this kind of approach?
I can't see it, right? Because it's not really it's kind of project agnostic, right? Because the LLM can kind of, no matter what you pass to it, the LLM will give you suggestions for labels, right? And then the same refinement process can work and all that. So I can't see a context where it wouldn't be used. Maybe if you have a really small project with only like a few components and you already know them and you don't think you need to, it's probably more suitable for larger projects, to be honest, because with smaller ones, maybe you just have the labels in mind you want to use and you're good. But yeah, this is probably more for larger scale projects, which have lots of components, and it's tough to know which labels you might want. So that would be what I would say to that.
Right. Or maybe like the domain of the project, right? If you talk about an art project versus a software project, of course, they're completely different things. You keep a human in the loop to refine this, right? There's a part I missed in the beginning. So you're not asking the LLM to generate the labels altogether. It's just a refining process with human validating what LLM outputs.
Yeah, so like I said to Emad, the LLM basically gives you the ideas for labels you want. And we have the process for kind of refining what you have, but that's the biggest thing is you don't have to start from scratch. So yeah. that's the idea there.
All right. Maybe a final one is, do you see that this can, and I'm interested in this because qualitative analysis, there's a lot of LLMs been helping on this, but there's a big issue with whenever you're labeling things, you're building knowledge, right?
Yep.
So do you see any potential limitation that I'm only based on what the LLM generates first, and then I might be missing important themes or concepts that I would otherwise have figured out if I have done the main work
Yeah, I mean
myself?
that's possible, right? I mean it's always going to be possible, but that's just the trade-off, right? Convenience for your thorough sort of. I mean, we all do it, right? When it comes to using LLMs for code generation or anything, that's always the risk of doing it, right? Is we're losing our own autonomy for things. But yeah, that's the trade-off for everything, right?
Right. Excellent answer. Thank you,
Yeah.
Liam.
Yeah, no worries.
All right. Thank you very much, Liam, for a wonderful talk. In the interest of time, I'd like to move on to Caren's talk. And then we do have a question in the chat from Rashna that maybe we'll get to at the end, Rashna, if you don't mind. But for now, I'd like to thank Liam for a wonderful presentation. And Caren, if you could share your screen.
Yes, let me share my screen. Yes, you should be able to see my screen now.
Yes, that's great.
Okay, perfect. So let me start. Hello, everyone. Today I'll be presenting my work, Bridging Design and Implementation, a study of multi-agent LLM architectures for automated front-end generation. In this work, we investigated how multimodal, multi-agent LLM systems can create dynamic applications from paired user stories and Figma designs. In addition, we also discussed how architecture coordination impacts the quality, cost, and reliability. I will start with talking about the motivation and the research gap, then discuss the research questions, then I'll present the multi-agent framework and the setup we did, and then I'll work through the results, and finally, we will conclude. The motivation for this thesis comes directly from my work experience in software development. In the real world, building a front-end application is a multi-step process, including multiple stakeholders. The process typically starts with the product managers. They work closely with stakeholders to understand user pain points and translate those needs into user stories. Then will come the UX designers who will take these user stories and translate them into mock-up designs, specifying layout, visual structure, and interaction patterns. And finally, we have the developers who are responsible for combining these two artifacts, the textual user stories and the visual mock-ups, to produce a complete dynamic application. And this leads directly to the core problem that we are addressing. This final step is cognitively demanding, where engineers must reconcile the two very different artifacts, the user stories and the Figma designs. The user stories describe the intended behavior of the system, but they are textual and often underspecified, while the Figma designs, on the other hand, describe the visual layout and spatial structure of the interface. Developers must mentally align these two modalities, the behavior and the appearance, while also resolving inconsistencies between them. As a result, this integration process is largely manual, time-consuming, and prone to errors. While this workflow is well understood in the practice, existing research typically addresses only parts of it, and that brings us to the gaps in the existing research. We were able to identify 4 different gaps: the single modality focus, the static UI generation, the lack of real-world evaluation, and the limited architectural analysis, which we will go through in the next slides. And the first gap, the single modality focus, much of the existing research in automated UI generation focuses on a single input modality. Some systems generate code from visual designs, such as screenshots or mockups, while others generate software from textual descriptions, such as requirements or prompts. However, real-world front-end development typically requires reasoning over the both modalities, the textual requirements where we describe the functionality, and the visual designs where we describe the layout. This disconnect motivates the need for systems that can jointly reason over both design and requirements. The second gap is the static UI generation. Beyond this modality limitation, another issue is that many systems generate static UI layouts rather than full interactive applications. Their goal is often to reconstruct the visual structure of the interface, focusing on layout similarity, such as structural alignment or pixel level similarity. However, real applications require dynamic behaviors such as event handling, state updates, and navigation logic derived from functional requirements. The third gap is the lack of real-world evaluation. Many existing studies rely on synthetic UI benchmarks or automatically generated design code pairs. While these data sets allow controlled experiments, they often fail to capture the complexity of real development workflows. Finally, there is also a gap in how multi-agent architectures themselves are studied. Recent work has begun exploring multi-agent architectures for software generation. However, most studies propose a single orchestration strategy without systematically comparing different coordination patterns. As a result, there's still a big lack in empirical evidence on how architecture choices impact generation quality, computational cost, and reliability. So in this slide, we are going to compare the relative studies and how they compare to our research. In this table, we summarize the key characteristics of the existing studies. We can see that there are systems such as Design Coder, Screen Coder, and UI Copilot where they only do design to code, while the other pattern we saw was in MetaGPT, AutoGen, and ChatDev where they just do like text to code. However, none of the approaches that we found jointly address both modalities while also studying the architecture coordination. So our work will lie at the intersection of these two lines of research. We will combine the textual user stories and the visual Figma designs within a multi-agent pipeline and evaluate how different architecture coordination strategies affect the generation quality, cost, and the reliability. Looking at these gaps, we saw an opportunity to explore multimodal LLM systems in a more structured way. Modern LLMs are capable of multimodal reasoning, meaning they can process textual descriptions, code, and visual layouts. At the same time, multi-agent systems allow us to structure complex workflows by decomposing tasks across specialized agents rather than relying on a single prompt. This combination enables us to study how multimodal generation pipelines behave under different architectural coordination strategies. This leads to the research questions that we're addressing in this work. So to study these challenges, we organized our research questions into 3 different themes: the quality, the efficiency, and the reliability. In RQ1, we focus on generation quality. We ask whether multimodal multi-agent systems can generate applications that align with both functional requirements and visual designs. In RQ2, we focus on efficiency, where we study how different architectural coordination strategies affect token consumption and output quality. And finally, in RQ3, we focus on reliability. We analyze the types of failures that occur in the pipeline and investigate how lightweight recovery mechanisms can stabilize the generation. We answered those research questions through a systematic evaluation. Our system mirrors real front-end development workflows. So in this section, we will talk about the agentic pipeline, the architectures, and the LLM as a judge. So let's start with a high-level overview. Our framework is organized around 3 primary agents: the builder, the validator, and the fixer agent. These agents generate, assess, and iteratively improve the React applications. Each agent maintains its own local memory and makes independent decisions about which tools to invoke. So let's talk about each agent on its own. For the builder agent, it is responsible for generating the initial React application. We have 2 inputs for our system: the user stories, which look something like this, where we say as a user, I can do something, and the Figma file, which is a mockup on how the system should look like. The builder agent will invoke multiple tools, such as the Figma tool, the story mapper LLM, and then the enricher LLM, which together will work to generate the React application. Then we will have the validator agent, which will evaluate the generated application. It will measure 2 different dimensions: the functional coverage, which assesses whether user stories are correctly implemented, and visual fidelity, which evaluates whether the interface matches the Figma designs. And then we will have the fixer agents, which will analyze the validator's feedback and applies targeted modifications to the generated code. This repair process will help resolve common issues such as formatting artifacts or missing exports or incorrect behavior. So to study this systematically, we implemented 3 different architecture strategies. We should note here that all agents and tools were identical across the experiments. The only variable was how the agents are coordinated. The first architecture is the supervisor model, where we have a single controller LLM, and then it invokes all of the tools. This architecture provides flexibility and adaptive reasoning, but as context accumulates, it can also increase the token cost and reduce consistency in longer reasoning change. The second architecture is the hierarchical architecture, where control is distributed across multiple supervisors, in this case, the builder, the validator, and the fixer ones. In here, we localize the context and improve the modularity, but it introduces coordination overhead and communication costs between supervisors. And finally, we have the custom architecture, where we remove the supervisor reasoning altogether. This workflow is encoded deterministically, and transitions are triggered directly. This eliminates the orchestration overhead and allows us to isolate the cost of supervisory reasoning altogether. This setup allows us to investigate a very important question. Does more supervision improve the results, or does it introduce unnecessary overhead? Despite the growing popularity of multi-agent systems, this trade-off between the supervision and efficiency remains largely underexplored. So to evaluate the outputs produced by these architectures, we implemented an automated evaluation framework using LLM as a judge. To evaluate outputs objectively, we separated the generation and the evaluation. One model generates the application, while a different model acts as a judge. Each output is evaluated along the functional and visual dimensions using a structured rubric with full, partial, or failed labels. To ensure the reliability of the judges, we validated the judges' consistency through an inter-rater agreement using Cohen's kappa. Now we can discuss the results of each of the RQs. So just as a reminder, the first research question was focusing on the generation quality. We evaluate how effectively the system produces applications that align with both functional requirements and visual designs. To measure this, we use two evaluation dimensions, the functional coverage and the visual fidelity. For the results, we saw that the system can achieve meaningful alignment between functionality and visual design. On average, models achieved 54% full functional coverage and 58% full visual fidelity. But when we include the partial matches into the numbers, we saw that the functional behavior increases to 77%, while the visual fidelity to 85%. This shows that multi-model, multi-agent systems can often align both behavior and layout simultaneously. An interesting behavior is that visual accuracy is slightly higher than the functional accuracy. This suggests that reconstructing the layout from Figma designs is more stable than generating dynamic behavior from user stories. This is expected because the layout reconstruction is largely structured, while functional behavior requires reasoning about state events and routing logic. We also observed variation across projects where simpler UI structures produce more consistent results, while domain-specific interactions reduce performance. Overall, these results demonstrated that the approach is feasible while highlighting the remaining challenge of dynamic behavior synthesis. While generation quality is important, we must also consider the computational cost of these systems. So for the second research question, we analyzed how different agentic architectures affect cost efficiency. Specifically, we measure token usage, including prompt and completion tokens. In addition, we compared the resulting generation quality in terms of functional coverage and visual fidelity against the consumed tokens. This allows us to study the trade-off between costs and performance across architectures. The results show that architecture coordination significantly affects the token consumption. The custom architecture achieved the lowest cost, reducing the generation token usage by up to 65% compared to the supervisor and the hierarchical, while maintaining the same accuracy. A key factor behind this token consumption difference is context duplication. Prompt tokens account roughly 60 to 70% of the total token usage, meaning that architectures that repeatedly resend context become significantly more expensive, while the completion tokens or the actual generation tokens remain relatively stable across the architectures. This means cost differences arise from how much context the architecture rereads, not from how much reasoning the model is actually performing. Another interesting observation is that the judge models dominate token consumption, using on average 5.9 times more tokens than the generators. This reveals that evaluation, not generation, is the primary scalability bottleneck in multimodal pipelines. And finally, for the third research question, we looked into the pipeline reliability and the failure modes. We examined 3 types of issues: the LLM refusals, the formatting artifacts in generated code, and how effectively our automated recovery mechanism stabilizes the system. During the generation, we observed occasional refusal behavior from the models. These responses typically contained phrases such as "I'm sorry" or "I cannot help with that," and I'm sure if you've used the models before, you've seen this. To handle this automatically, we implemented a keyword-based refusal detection mechanism combined with a retry strategy, allowing up to 3 attempts. This mechanism successfully recovered 29% of initially failed generation and leaving only 9% that are unrecoverable. Other than the refusals, we also analyzed the formatting artifacts. The most common issues were the postcode text, the code fences, and the pre-code text. In many cases, the LLM wrapped valid code with conversational text, which led to compilation errors. Structural issues such as missing exports or missing files were comparatively rare. We also detected excessive comments and removed them to reduce token consumption. The key point is that most failures were structured. Because these artifacts are predictable, a lightweight cleanup mechanism was sufficient to stabilize the pipeline without requiring regeneration. So, to discuss everything we've been through, first, the multimodal generation works, but it is still imperfect. The system can generate applications aligned with both design and functionality, but performance decreases as interaction logic becomes more complex. Second, architecture simplicity improves the efficiency. In our experiments, we did see that simpler architectures, such as the custom, often matched or outperformed the more complex hierarchical or supervisor architecture. This suggests that additional coordination layers can introduce overhead without improving output quality. Third, the evaluation dominates system cost. The judge models consumed significantly more tokens than generators, indicating that evaluation may become the primary scalability bottleneck. And then finally, most reliability issues were formatting artifacts rather than reasoning failures. Overall, these findings suggest that scalable front-end automation depends not only on model capability, but also on efficient architecture design, evaluation strategies, and practical reliability mechanisms. So let's walk through some examples just so you see what I'm talking about. On the left, we see the design input extracted from Figma, and on the right, a screenshot from the compiled React application that we generated. In this example, the system was able to successfully reconstruct the landing page. Navigation elements were set, and the content and structure was all aligned. Another example we can go through is a dynamic example. On the left is the input that we gave our system, which is a filtering mechanism for houses. And on the right, we can see the user story where it says, as a user, I can search by location or number of bedrooms. We can see here that the behavior actually worked. If you put a price that doesn't exist in the list, it will filter out all of the houses in the list. Same for the number of rooms or the location. So to conclude, this work makes 3 main contributions. First, we show that multimodal, multi-agent systems can bridge the gap between design and implementation by generating dynamic React applications from paired user stories and Figma designs. Second, our results demonstrate that architecture simplicity can outperform more complex coordination strategies. Finally, we show that reliable generation pipelines are achievable. Most failures were formatting artifacts rather than reasoning errors, and lightweight repair strategies significantly improved the stability. Overall, this work provides new insights into how architecture design influences quality, efficiency, and reliability in multimodal LLM systems. So for the future work, we first plan to explore architecture coordination strategies across different multi-agent frameworks, such as AutoGen or Agentverse. Second, we would like to evaluate whether these architecture trends generalize to other software engineering tasks beyond the front-end generation, such as testing. Third, an important extension would be a full-stack generation to see if the system can integrate front-end with back-end services. And finally, we would like to see if it can scale the multimodal benchmarks by constructing larger data sets of paired user stories and design artifacts. And thank you, and I'll open the floor for questions.
Thank you very much, Caren. Great presentation. I should also mention that Caren recently successfully defended her master's thesis, so congratulations for that.
Thank you.
And she's also going to be presenting in Rio de Janeiro at MSR, right?
Yes.
For anyone who's planning to attend ICSE or the related conferences, I hope you'll go take in Caren's presentation. Diego, you have a question.
Yes, thank you, Caren. It's quite timely for me because I actually need to reconstruct the Concordia daycare website. So as a parent, they tasked me to do it. So I'm going to be asking you a few questions. The first one is that you have the accuracy, seems to be, is that an average? Because you probably try, I don't know, different models, different like architectures, right? But you showed in the slide there just like one single bar with full match, partial match. Can you elaborate a bit more on this?
Yeah, exactly. So we did try 3 different models with one GPT, one Claude, and Gemini. And we used the newest ones when I started working on this project, which was last May. So this is the average across all of the different models, across all of the different projects, and across all of the different user stories. So we did have 75 different user story pairs where we have like the mock-up and the user story. So this is an average of everything together.
Right. Is there a big variance? Or maybe a different question would be, would you recommend me one solution in particular that you saw was, doing pretty well?
A specific model.
A model or architecture, like where should I start
Mm.
if I have to do this as I do?
Yes, so for the architecture, I highly recommend the custom one where you don't like add a lot of supervision because that would cost you the least, but it had still the highest quality. For the models, I'm pretty sure it would really depend because the ones I started with, like I said, were out last May. So since then, there's a lot of newer models. So it would really depend on when you're starting the project. But from the results that I had, Gemini had the best results. So maybe go with the newest Gemini.
All right, very good. And maybe I don't see any other hands. I just wanna, the custom I would assume is customizable, right? So that you just took something from the architecture that they say, okay, here you can just change as you'd like. So this is what you'd call the default custom, like what comes out of the box as a custom?
So the custom is something that I created.
Okay.
Let me go back to the architectures just quickly. Um, so there we go. Okay, so these are all LangChain architectures that we looked into just because it was way easier to implement, right? But the custom is basically you create your own agents and you decide how they're going to interact with each other. And that's why they costed the least because it was deterministic. We say after the builder, always invoke the validator, and after that, always invoke the fixer. While in the hierarchical and the supervisor, we did not have that determinism, where the supervisor is the one who's choosing which agent to call next.
Right. So this is already you bring some expertise, what you've learned to propose something, and you call it custom. Excellent. Thank you.
Thank you.
Any other questions for Caren or comments, feedback from the group? Wow, everybody's so quiet today. Oh, Roshna, I see you're back.
Hi, Caren. Thank you. Thank you for a great talk. I mean, both talks were so good and interesting. I'm very happy to listen these talks. A kind of praise I would like to give you for this work because I have been working in front end and always I used to create the UI from the Figma designs and I used to feel that okay, it's matching more. I mean, if you go to slide 33, so I used to create something like what LLM is creating, but I used to get feedback that, oh, the padding is not matching the color, the fonts, the alignment is not proper. And these things my eyes never used to catch and still doesn't catch. So I wish if LLM could handle these kind of CSS intricacies, developer will really praise, and many backend developer will start loving front-end development. So nice work. I mean, thank you for this talk.
Thank you so much, Rashna. A tip, I guess, something that I learned while working on this is that Figma has an API that you can call to kind of get the HTML tree of the website. And from there, it's very easy. Well, it is easier to kind of grab the CSS, right? If you want like the colors and the fonts and the things that your eye is not going to catch, like you said. So you can also
Yeah,
try
but
that
sometimes
next
it
time.
contradicts, no? Sometimes it contradicts very differently. I don't
Yeah,
know.
but with LLMs, it's now easier to just tell the LLM to kind of change that HTML to kind of a proper website.
Okay, thank you. Does anyone else have any other questions for Caren? Rashna, I know that you had another question that you put in the chat for Liam's presentation. So if nobody has any other questions for Caren, we could quickly address that question before I let everybody go.
Lori, maybe I have a quick question for Caren.
Okay.
So Caren, thanks for the nice talk. I guess what I wanted to ask about is this notion where you're sort of starting with the Figma, you're starting with the user stories, and then you produce what what a user would want, the application that the user would want. Now, in some other cases, I think this is like an excellent, let's say, flow of how we build apps today, right? As we get more and more AI in these in our development pipelines, let's say, people are actually looking for AI to innovate, right? So not just that we give it something and it produces what we give it, but can it actually give me like different designs? Can it give me optimal designs? Do you see that, or how that might work with the framework, let's say, that you're proposing? Do you think that that would work,
Yeah,
or
I think.
or do you think you absolutely would need this Figma and user stories to come out on an application, come out to an application?
Yeah, that's very interesting, actually. I think, what would be interesting to try is to kind of give it this as a base and ask it to, like you said, be creative and see if it can make it better.
Mhm.
But UX is very it differs from one person to the other, right? So
Absolutely.
there's no right answer. So I guess like just getting ideas from the LLM might be a good way to just see different options and then maybe pick and choose what you want from these different options to create your own custom UI. That would be interesting to try.
Perfect. So you fell into my trap. So my follow-up question is, so in such a case, what architecture do you think might actually be the best? Like, because I think the architecture would matter a lot in such a case, because it would be very, very different than what you're doing now. Do you think that that might have an impact?
Not for this use case. So for this use case, I think the custom would still be a good one to go through because there is no like iteration or there is no, because you're just telling it to use this as a base and give me options. I think if different architectures would be better, in my opinion, but we didn't try it, right? To maybe do add some backend integration because then like being able to connect the front end with the back end might produce a lot more errors. So you maybe need that more extra coordination to deal with all of
Mhm.
these issues.
Yeah, yeah, and just absolutely. And I think maybe just real quick, I think also you might want to go through a few designs, right? And so in such a case, I think probably some sort of more supervisor and going back and forth into these designs might be an interesting one. Anyway, it's just an idea that I think might be worth exploring
Yeah.
further as you change the use case, I guess. But anyway,
Mhm. Yeah.
thanks, Karen.
Thanks. Thank you.
Thank you so much to both of our speakers today. It was a pleasure to hear your research talks. I'm going to let everybody go because it's 11 o'clock and I know people have meetings and other things to get to. But Rashna, if you wouldn't mind connecting with Liam about your question, that would be great.
Sure. I'll talk to Liam.
Okay, wonderful.
Thanks. Thanks,
Thanks,
everyone.
everyone.
Thank you very
Thanks
much.
everyone for
Everybody.
listening.
Have a great day.
Thank you.
Everyone.